there were a couple of things we needed to, oh, okay, so remember, just as a basic review of last class, we basically talked about there was two types of alkynes, internal and terminal. And we did some chemistry with regard to these. So terminal alkynes with say HBr, one equivalent. Second equivalent. Whoops. I'm not adding the little lone pairs here for this. So this was basically one of the questions we had at the start of our, and then and we talked about these reactions, and we talked about brominations, Br2, and actually let's do the other one first. Second equivalent would give us the I think that's basically what we did last class. Now, the other fun reactions that we need to think about are the addition of H2. So when we did the addition of H2 with an alkene, what were the key features with regard to this? When we're adding H2 to an alkene. So if we had, say, this, and we added H2 with palladium on carbon, and we had some solvent, what was the main thing which happened here? Right, both H's added to the same side. So we would end up with because the H's in this case were absorbed on the surface of a metal, and they would add on the same side if this was your double bond. Okay, and then the nuance to this was that if you had a double bond which had some big bulky group somewhere, that would be on the opposite side. So if we had, I don't know, I'll put a tert butyl group somewhere and did the same reaction, we would have the methyl groups would both be on the same side as the tert butyl now, because the hydrogens had to add on the opposite side. Yeah, so that's basically what we needed to do with alkenes. Now with alkynes, there's something which is interesting here. So if we have, and let's do it with the internal. So there's actually two different products that are conceivable from this. If you add one equivalent, and I'll put in quotation marks, one equivalent of HH. We could have a stereoisomer that looks like this, or we could have a stereoisomer that looks like this. So we could have cis or Z, or we could have trans or E as possible products. And of course, chemists have developed ways to make each of these. So it depends upon the reagents that we're using to actually do the reduction, which will be the key factor here. So, and if you have a terminal alkyne, and you use one equivalent of HH, put that in brackets because it doesn't necessarily mean it's coming from molecular hydrogen. It could, the H's could come from different places, but H is being added to each carbon. Oops. So if we do this reaction, there's basically only one possible product because H's are going everywhere, right? So it's still a mono-substituted double bond. Okay, so this one is, the terminal one is terminal. This reaction is, in a way, and I'll put it in brackets, less interesting. Because there's only one stereoisomer possible. So let's talk about how we add HH to double bonds. So the first thing which is interesting is that if we had, if we used, the reagents that we used for alkenes, which the most common one was palladium fused on carbon with H2 gas. When you use these reagents with an alkyne, and it doesn't matter which kind we've got, so this, let's say we do this. We add H2, palladium on carbon, we'll use some alcohol as the solvent. If we're using palladium on carbon, would we expect, which of these two stereoisomers up here would we expect to make if we were using a metal-based catalyst? Should we be making this one or should we be making this one? Yes, they should both be on the same side. It's the exact same principle as we had before. So the if the hydrogen's absorbed on the surface of the metal, we should expect to make this. Now the trouble is, you do make this, but this is it's, the reduction is so fast that you can't really isolate this product, and you end up making the alkane. The catalyst itself is too reactive, and so the second equivalent of hydrogen adds, and you end up with the alkane. So if you have a triple bond and you use palladium on carbon, you just do the reduction and it goes all the way to the alkane. So that's a bit unfortunate. So the trick was stopping the reaction. We need to stop here. And someone did develop a synthesis to do that, and that was basically a Lindlar research group. You always, if you discover something, you get your name on it. So if you use Lindlar's catalyst, you can do the reaction. So H2 and we just Lindlar. And you end up with a cis Cisalkene. Now, Lindlar's catalyst is very similar to palladium on carbon, except for it's not on carbon, it's on calcium carbonate, and it's poisoned with an alkaloid. I think it's quinoline, and so it just reduces the reactivity of the catalyst, and it stops at this stage. So Lindlar's catalyst is how you end up with a cisalkene. So that's basically what you would do. It's very similar to, so that's great. If you had a terminal alkyne and you use the same thing, you would end up with a monosubstituted alkene. So H2 and Lindlar. So what we'll do is we will see this very frequently. So hydrogen absorbs on the surface, the triple bond comes down, forms a pi complex, the hydrogens sort of transfer over and you end up with cisalkene. So that's fun. You don't really need to worry about the mechanism too much. It's just that catalyst is the best for making a cis double bond. Now, to make a trans double bond, we're going to do something entirely different, unless there's any specific question. So with palladium on carbon, it gets over-reduced to the alkane. So that's useful. With the triple bond, eternal triple bond, you make the cis through Lindlar. And to make the trans double bond, we are going to use something. We are going to use a reducing metal reduction. So with this, we use our lithium or sodium in ammonia. And our product is trans/E alkene. And this reaction is it's a radical reaction. So this is basically a radical reaction. And we'll do the mechanism of this just because it's interesting. So the NH3 is the solvent. It's also, the other thing we know about this is that it's a pretty strong base too. So this is the salt, oops. This is the solvent, but it is basic. So this, your whatever group, other functional groups you had in your molecule, if they're sensitive to base, that would be slightly problematic. So there's some limitations with regard to this. But the mechanism is interesting in the sense that, and with lithium or sodium, this is the metal. It's not the cation. So we're not throwing in lithium plus or sodium plus. We're throwing in lithium with the electron or sodium with the electron. And so what they're going to do is they're going to donate their electron to become Na plus or lithium plus. So this is how, so they're going to be giving up their electrons so they can attain the Nobel gas configuration and carry a positive charge. And so what we're going to do is we are going to add our electron to the pi system. So I'll just put metal here with dot. And if we add our electron to one carbon, that means that these other two electrons are going to move over to the other carbon. And we're going to have this. And that's going to be a negative charge. So if we were to draw this, let's draw this. All right, now we're going to shade in these orbitals, because that's the pi bond. And so our electron I tried to draw that. I should have drawn it actually not as a zigzag. Anyway, let's draw it more. Let's do it like this. Because these electrons are now in sp2 hybrid orbitals. So we'd have two electrons here, one electron here. This would be the anion. That would be still a radical. And so there's two configurations that these could actually be in. And let's draw it. Going back. Here's our p orbitals. And this is and so, and if we were to look at this from above, this is probably the better way to draw it, we would have the orbitals that we'd be looking down upon would look like that. And the background underneath it would be the other lobe. Oops. Those little dashed lines at the bottom lobe here, if you're looking straight down. So, and so if this equilibrium here basically isn't, one conformation is more stable than the other. You can think of it in two ways, actually. The first, which would probably be would be that in this conformation here, these two R groups are sterically hindered, like they're larger. The other way you could think about it is that with the electrons, repulsions, the electron repulsion would be greater in this conformation as well, like these electrons with these electrons. And so when you've got sterics and electron repulsions, the favored conformation would be the one in where the two R groups are on opposite sides. And so from here, now the solvent's going to play a role, because we would have said to ourselves, oh my, we've got a carbon with a negative charge. That is pretty reactive. And that's Right. So here we would protonate. We're going to grab a proton from the solvent, which will give us this. And then the metal is going to donate another electron to the, it's going to react to that orbital here with the other electron. And then we will protonate again. Oops. So this reaction in the end, when you think about it, we're going to have some NH2 negative floating around with some lithium plus or sodium plus. And this reagent is extremely basic as well. So if you've got any acid sensitive groups, they're going to react pretty quickly. So, but in the end, you end up with a trans alkene. So trans. So yeah, this relies on, and one of the advantages of when you're using like ammonia, this is basically, this is a gas, but it condenses at like at minus 20 degrees, I think. And so you can run this reaction at minus 40, and then you can remove the cooling bath, and then all of the solvent evaporates, and you end up with your product plus some salts, which you can just hydrolyze with water and extract out your product. So it's quite a, in some ways, it's, if you're used to working with this, it's interesting. Plus, the colors are very interesting. When you solvate electrons in NH3, it produces some pretty bright colors. If you do inorganic chem with Dr. Yan, you'll do this reaction, which can be quite spectacular. So not this reduction, but just to reduce solvating an electron. So that's basically how this works. So lithium or sodium in NH3, and you'll get your transalkene. So you've got a method of, with an internal triple bond, you've got a method of making the trans. The cis, or if you want to, just the alkane. So H2 and Lindlar, H2 palladium on carbon, or sodium NH3. Now the fun thing is later on we're gonna, and I've put two R groups here. We could make this, I could just call this R primed on one of them. The fun thing is later on we're gonna find out how to install an R group on each side of a triple bond. And so this is going to allow us to make a whole bunch of potential products. And of course, we've already seen in the last chapter all of the fun things that we can do with double bonds, right? There's all of those reactions we can do with double bonds. So HX, water, like epoxides, cyclopropanes, all of those fun sort of things. So we're gonna learn how to make some pretty complex molecules out of some really simple basic starting materials. And that's kind of fun. So that's basically how to reduce a triple bond to a double bond. Any questions on that? Okay. Well, what we do next? Right. Okay. So then, the next part will be adding water. So when we were doing alkenes, there were basically two different mechanisms, two different reagents we used to add water. One was the BH3 the hydroboration. And the other one was when we had the mercury, HgOAC2, then why are you doing that little sorry, I've got more solvents there. Make this arrow bigger. Okay. One was the hydroboration, one was the oxymercuration. So the oxymercuration was the Markovnikov because the carbon with the most protons got the proton. In the case of the hydroboration, this was the anti-Markovnikov. Anti-Markovnikov, because in this case, the carbon with the least number of protons ended up getting the proton. And the hydroxy group went on the opposite carbon. So, and the neat thing about the hydroboration was that both the H and the OH were on the same side. Now, with alkenes, we're going to see that this is very, very similar. The oxymercuration reaction is a bit simpler. The hydroboration reaction is exactly the same. So let's do the hydroboration first, just because it's identical. So now, when it comes to an oxymercuration or a hydroboration reaction with an alkyne, the ones which will be interesting are the terminal. because one carbon has got a proton and one carbon has got a carbon. So if it's an internal alkyne, neither carbon's got a proton, because these two reactions are a Markovnikov reaction and an anti-Markovnikov reaction. So we need a proton attached to a carbon to make it Markovnikov versus anti-Markovnikov thing work. So with the terminal alkyne are, if we were to do the first step, BH3 and THF, we would get, remember the boron and the proton add on the same side, BH2. This would be our intermediate. And then the second part is the conversion of the carbon boron bond to a carbon oxygen bond. And this would be our product. Now, what's interesting is that this, I'll redraw it over here. This type of compound where you've got a hydroxyl group bonded directly to an alkene has got a special name. And its name is an enol. OL for alcohol, ene for alkene. Now, enols are not stable. So the key point here is these are not stable. There's one type of alkene which is stable. Well, there's a couple, but the most popular type of alkene that is stable is something which we would call something entirely different. And that would be this. This would be a phenol, right? And it's got the same structure here. But they are stable, and it's stabilized because of the aromatic ring. So we'll talk about those later on in the course. But simple enols aren't stable, and so they revert to a more stable form. So this is actually an equilibrium. This big arrow. And so the more stable form is this. Oops, wrong way. And we know what this guy's called because this is an aldehyde. Now there's this process here when you convert an enol to this functional group here is an aldehyde, but the form, which the carbonyl form is sometimes called the keto form, but it's not necessarily a ketone. Sometimes it's an aldehyde. So this process from going from an enol to the keto form is what we call tautomerization. Now, the way that we would draw how this works is I'll draw the arrows, but it's technically not correct. But I'll do it anyway because just to help people visualize how this might work. So we need to make a carbon oxygen double bond, and we need to make a carbon hydrogen bond. And so one way of drawing this would be to have these electrons go here, and the electrons in the pi bond go up and grab that, and those ones go there. But that's technically not what's going on. Or you could even simplify it by doing this, I suppose. Let's draw the proper way. And the reason why this tautomerization takes place, it has to do with bond strengths and all that sort of stuff. So if you do an analysis of this, one form is actually thermodynamically more stable than the other. And so that's why this happens. This is a simple way of drawing these arrows, but it's actually not correct. It probably takes place intramolecularly. So, but anyway, so anytime you've actually got a ketone or an aldehyde, so let's just draw these. They're actually in equilibrium. There will be a small amount of enol in each. Like if you had a bottle of acetone, typically for every, I think it's 100,000 molecules of one, you'll have one molecule of the other tautomer on average. Certain carbonyls tautomerize more quickly. Aldehydes seem to tautomerize a bit easier than ketones. But the general rule is for every 100,000 molecules of the keto form, there'll be one molecule of the enol form. Something like that. So it's just, and in fact, with ketones, you can have two different types of tautomers if it's unsymmetrical. Sorry, two different types of enols, because we could have drawn it like this as well. Anyway, so the neat part about if you do a hydroboration of a pH3 THF, step 1, step 2. You end up making an aldehyde. So that's interesting. And so the carbonyl goes on the carbon with the proton. So this is a anti-Markovnikov addition. And so what we're going to see when we do the oxymercuration is exactly the opposite. We're going to end up making the ketone as opposed to the aldehyde. So let's do the oxymercuration. Unless there is a question immediately, or unless there's a question. Okay, so Now, with the oxymercuration of an alkyne, the reagents people use aren't quite the same. It's just mercury sulfate and you need acid. So the common acid that people use is sulfuric acid. You need a bit of water in here as well. Plus you need to dissolve there might be a co-solvent as well, but most textbooks just put H2SO4 and water. So we're still using, if you think about mercury acetate or mercury diacetate, the mercury in this case is mercury 2+. And with mercury sulfate, this would be mercury 2+ as well. So it's still using mercury 2+ as the reagent. There is no reduction in the second step. So if we've got a terminal alkene and you use HSO4, H2SO4, and water, you end up with the acid. I basically, because you would think, well, wait a second, there's I'll just put mercury plus here. This bond is converted, gets protonated really quickly. So the mercury is, we don't have to worry about reducing off breaking that mercury carbon bond. This is exceedingly weak in these circumstances. So you end up making, the mercury disappears from it. So it just goes directly to the enol. And so, and when this tautomerizes, the carbonyl is on the more substituted carbon. So the carbon which had the proton gets the protons. So this would be a Markov. Technically, this would be a Markovnikov. And so this would be a ketone. And specifically, we've got a methyl group on one side, it would be a methyl ketone. So the addition of water to triple bonds, one gives a ketone, a methyl ketone, the other gives an aldehyde on the last carbon. We don't see, well, we wouldn't do this reaction too often with, say, a internal alkene, unless it was symmetrical. Because in this case here, it doesn't matter which one you do. Let's do the hydroboration reaction, H2O2. So this is with an internal. There'd be two products you could make. Because no carbon has got a proton, you would get a mixture of you get a mixture of these two, and then when they tautomerized, you would have our you'd have two products. So you should get 50% this and 50% that. And just think, when you're in the lab and you have to recrystallize your compound, you think to yourself, oh my God, I'm in the lab and I've got to recrystallize my compound and I'm going to be here another hour when I could be going home and it's cold outside. This sucks. Now, that's when you're working with something which is relatively pure and has a couple of impurities in it. And just imagine if you've got 50% of this and 50% of this, and you've got to somehow make one of them pure. Your yield is going to be at maximum 50%. And you got to take the time to separate things out. Not good. So organic chemists don't like doing this. So this reaction isn't particularly useful on an internal alkyne unless it's symmetrical. So if you had, say, this, and you did this reaction, that's fine, because what you're going to end up with is the same thing. These are the same. So that works fine. But if it's asymmetric, if it's not symmetric, then this reaction isn't particularly useful. So just keep that in mind. Now the fun thing is later on, we are going to see what you can do with carbonyls, particularly ketones and aldehydes. These are really useful functional groups for a whole bunch of fun stuff we're going to do. So yeah, to be able to convert a triple bond into a carbonyl, yeah, that's going to be a useful reaction. So that's good. That's very good. Let's see. Now there's basically probably two other reactions that we could do in this section. So actually, we'll probably, if we finish it off today, that means on Thursday, we could use Thursday as basically a big giant review day for the midterm. Does that sound like fun? Okay, good. So that's what we'll do. Okay, so the two last reactions we're going to do is, okay, so last two reactions. Okay, one of them is, we'll do the first one really simply right off the bat, ozone. Okay, so when we had a double bond and we used ozone and say triphenylphosphine or zinc or dimethyl sulfide. Remember, this reaction basically chopped a double bond in half. And so it would produce two carbonyl compounds, and they would be, so I'll call this carbon 1, carbon 2, carbon 1, carbon 2, carbon A, carbon B, carbon C, A, B, C. So we chop our molecule in half, and I'll call this carbon 3, I guess, 3. It would chop our molecule in half, and you would generate aldehydes or ketones. So let's do this one. And our two fragments would be now usually you'd only want one of them. So this is 1, 2, 3, 4, 1, 2, 3, 4, and the other side will be A, B, A, B. It might be that when you're doing this reaction, there's one part that you want, and you're just trying to make a ketone or an aldehyde, and that's when it would be useful. Now, when we're dealing with alkynes, however, and we do the same reaction. So I'll just put an aromatic ring here just because. Actually, I'll do two examples. If we were to use ozone, the workup for this one, I think it's similar. We'll just, I should check my notes on that. In fact, I don't even know if you need it, but I'll just write it down because just for the sake of argument. When you chop this off, you'll notice that you've got 1, 2, 3 bonds. 1, 2, 3. So our product is going to need 3 bonds to oxygen. So when we do this, 2 bonds to oxygen, 3rd bond to oxygen. So 1, 2, 3, 1, 2, 3. You end up making carboxylic acids. Actually, there is a way of making carboxylic acids from double bonds. It's using a really powerful oxidizing agent, and that would be potassium permanganate. And this would make carboxylic acids as well. This KMNO4 is a super powerful oxidizing agent. It chews up all sorts of molecules. So synthetically, it's not super useful, but on the rare occasion, it's used. The difference is, though, so it would oxidize any carbon which had a proton on it. So these ones would all be oxidized. I'll write them in. How will I highlight them? I'll highlight them in this. So this carbon would be oxidized, this carbon would be oxidized, this carbon would be oxidized. It doesn't oxidize ketones. So aldehyde, if you had KMNO4, this would become a carboxylic acid. But the ketones would stay ketones. I won't bring that up too much, but a lot of organic textbooks do bring up potassium permanganate. It is a test to test for double bonds. It's because it's a purple color. You add a couple drops of potassium permanganate, it turns into an ugly brown color. But anyway, this other reaction here, the alkynes, this is an interesting, so you make carboxylic acids through that. You'll notice that when in the course of this reaction here, you've got 1, 2, 3 carbons, 1, 2, in this case 2, 1, 2, 1. The other fragment which is lost in the process is actually carbon dioxide. So when you've got a triple bond, a terminal triple bond, you'll actually make carbon dioxide in the process. It gets, it's the one thing which can get oxidized even further. So, yeah. So that's, so with alkynes, ozone will produce carboxylic acids. And we'll see later on that carboxylic acids can be used to make a whole bunch of other fun things too. Okay. So that's the first reaction. The second reaction is going to take us back to, and this is only useful for terminal alkynes. There was something that was in way back when we were talking about what is the strongest acids, A, B, or C? Way at the start of organic 1. But what was the strongest acid here? C, that's right, because of atomic size, right? Atomic size. As you went down the periodic table, okay, and if you had, say, H, A, E, or C, so in this case, it's C is the right answer. In the second one, what's the strongest acid? Right, B, and that was because of electronegativity. All right, and how about this? A, B, or C? Which one of these was the most acidic? This one, we've got a mix of different answers, and the correct answer is C. And this had to do with the type of orbital. So in A, all of the carbons are the carbon's sp3, in B it's sp2, and C it's sp. Sp carbons are the negative charge is stabilized by an orbital that is closer to the nucleus, got more S character, all these sort of answers. Remember to take group theory, Dr. Yan, and he will tell you the real reason. It's all about molecular orbital diagrams. But anyway, so the protons on an sp orbital, so the pKa of an sp3 was approximately 50, pKa of sp2 approximately 45-ish. The pKa of an sp orbital is approximately 22, if my memory is correct, 20 to 22. So it is far more acidic. So it makes them easy to remove with strong bases. So you can take a, I'll just put a bar here. Your textbook, the base your textbook uses all the time is sodium NH2. So what this is would be would be NH2 minus sodium plus. And we'll use an aprotic solvent because you wouldn't want your solvent to protonate your NH2. So the pK of NH3 is approximately, I think, remember, my memory is correct, 32 to 35, something like this. So it's easily capable of deprotonating your carbon. So in this case, we would make, and I'll put a little sodium plus beside it. So that carbon's got 2 electrons and a negative charge. Okay, now a more practical base, and I realize we're running out of time here, is this guy. What was its acronym? Right, it was LDA. Right, so this guy is LDA. So do we remember what was interesting about LDA in organic 2 just before, or sorry, in organic 1 before we sign off for the day? LDA was when it came to nucleophiles versus bases, it was always a base. Because it was the isopropyl groups were big and bulky and that sort of stuff. Make this in THF2. So, and it's a practical base to use. Anyway, so although most textbooks use NaNH2, that's not really it's not a super practical base to use. LDA is far better. So anyway, it can deprotonate that carbon. And so this is basically the equivalent of R. But technically, the lithium carbon bond is a covalent bond. It's just so I'm going to draw, I just drew it like this. Now, we've run out of time, but at the start of really what this is used for is you can do SN2 reactions with this reagent. Because remember, this was a nucleophile. Carbon with a negative charge. Okay, so that's a good nucleophile. The other part which made it a good nucleophile is that it was linear, right? Because there's not much steric hindrance because of that triple bond is linear. So there wasn't a whole lot of steric hindrance, but it's only good for SN2 reactions. So it works well with primary alkyl halides and methyl, like methyl X, whatever it would be. With secondary alkyl halides, it doesn't work very well because you'd have to really be careful with how you did the reaction, mainly because you could get some elimination reaction. So what we're going to see is that you can do some alkylation reactions with primary alkyl halides. So it's a 2-step process. The first step is deprotonating it with LDA, and the second step would be using something like ethyl iodide, and you would make ethyl. All right, so what we'll do, so just take a look back at some of your SN2 reaction type of things. Just refresh your memory that it's primary alkyl halides and methyl, excuse me. And it's really just a 2-step little process how to do that. But what we'll do next class is maybe if you have any questions, bring them. I will I'll open up the Moodle stuff for an old midterm. I'll give you the answers to the practice sets, and I'll open up the review questions on Top Hat. But if you have any questions, bring those, and then maybe what we'll do is we'll just do a big giant review section, and I can just answer questions or quiz you type of thing. I don't know if I'll be able to quiz you with like necessarily with top hat questions, but I'll be able to draw stuff on the thing, and then you can write down what you think it is and mark your own work. All right. Were there any questions before we go then? Sorry, I'm like 5 minutes late. Okay, well, if not, have a good class, have a good day, and I'll see everybody on Thursday. Super.
Thank you.
You bet.